Hello, myself Ramya Kadapanavar. Now I am going to cover the topic about compressibility factor, which includes the definition of compressibility factor, generalized charts for compressibility factor, eccentric factor, and Pitzer correlation. Now we will discuss about the compressibility factor, which is denoted by Z. It is a dimensionless quantity that measures the deviation of a real gas from an ideal gas. The formula for compressibility factor Z is equal to volume of real gas divided by volume of ideal gas at temperature T and pressure P. As we know, the equation for ideal gas PV is equal to nRT. From this, we will get volume of ideal gas is equal to nRT divided by P. By substituting the volume of ideal gas in compressibility factor formula, we will get Z is equal to P into volume of real gas divided by nRT. Now we will discuss the values of compressibility factors for some gases. For ideal gas, Z is equal to 1, which means there is no existence of a real gas. Hence, volume of real gas is equal to volume of ideal gas. For real gas, we have two scenarios. The first scenario is Z is less than 1, which means the attractive forces between the gas molecules pull the molecules closer together, which causes the decrease of volume. This is more likely to occur at low temperature and moderate pressure. The next scenario is Z is greater than 1, which means the repulsive forces between the gas molecules push the molecules apart, results in the increase of real gas volume. This is more likely to occur at high pressure and high temperature. From this, we can say that volume of ideal gas is greater than volume of real gas. Next, we have virial expansion for compressibility factor in terms of pressure and molar volume. The first one is virial expansion for Z in terms of pressure P. Z is equal to 1 plus B dash P plus C dash P square plus D dash P cube plus and so on. It means Z is directly proportional to the power of pressure. If pressure increases, the compressibility factor will also increases. The next we have is virial expansion for Z in terms of molar volume. Z is equal to 1 plus B divided by V plus C divided by V square plus D divided by V cube plus and so on. From this we can say that Z is directly proportional to 1 divided by the power of molar volume. If the volume increases, the compressibility factor will decreases. The above both equations are known as virial expansions. Virial expansion means it is a power series that relates the compressibility factor Z of a real gas to its pressure P and molar volume V. The parameters B dash, C dash, D dash and B, C, D are called virial coefficients. Now we are going to discuss the graph which illustrate the deviation of real gases from ideal gas behavior. At low to moderate pressure, the curve for most gases, here we can observe for N2CH4, O2, CO2 dip below, which means those curves are under the ideal gas behavior. This is because here the attractive force between gas molecules are dominant. Hydrogen and nitrogen shows the least deviation. The curve for H2 is always above the ideal gas line, which means here repulsive forces are dominant even at lower pressure also. Methane, oxygen and carbon dioxide shows more significant deviation because these gases have stronger intermolecular attractive forces compared to H2 and N2. Eccentric factor. It is a dimensionless parameter used in thermodynamics to measure the deviation of a fluid's vapor pressure behavior from that of a simple fluid. Simple fluid means a hypothetical fluid with spherical molecules like a noble gas, xenon, krypton, radon, which has an eccentric factor of 0. Some important points. It was introduced by K.S. Pitzer and by his co-workers. It is a third corresponding state parameter often used in reduced pressure and reduced temperature. It is a characteristic of the molecular structure of a pure chemical species. The formula for eccentric factor is omega equal to minus logarithmic reduced pressure plus 1 at reduced temperature is equal to 0.7. Now we have this graph, approximate temperature dependence of the reduced vapor pressure. In this graph, x-axis represents the reciprocal of reduced temperature and y-axis represents the logarithmic of the saturated vapor pressure. In this graph, we can observe that for pure fluid, the graph between these two is almost straight. It means it is linear. But in real life, it is not true because each fluid has its own characteristics value of S. The slope of this graph is d of log reduced pressure divided by d of 1 divided by reduced temperature. The observations for above graph. Pitzer noted that all vapor pressure data for simple fluids like argon, krypton, xenon lie on the same line and line passes through at reduced pressure equal to -1 and reduced temperature equal to 0.7. The relationship between the vapor pressure of a complex fluid and a simple fluid can be fixed by a parameter, that is, logarithmic of saturated reduced vapor pressure for simple fluid minus logarithmic of saturated vapor pressure. From this, we can say that all fluids having the same value of omega when compared at the same temperature and pressure have same value of compressibility factor and all will deviate from ideal gas behavior about same degree. Now we have Pitzer correlation. Pitzer correlation for compressibility factor, that is Z is equal to Z to the power 0 plus omega into Z to the power 1, where Z to the power 0 and Z to the power 1 are the functions of reduced temperature and reduced pressure. In this we have two cases. First one is for simple fluids. For simple fluids, we know that omega is equal to 0. By substituting omega is equal to 0 in the compressibility factor equation, we will get Z is equal to Z naught. Case 2. For non-simple fluid, Z to the power 1 is a function of reduced temperature and reduced pressure. For second virial coefficient, the Pitzer correlation is BPC divided by RTC is equal to B to the power 0 plus omega into B to the power 1. Let's consider this equation as 1. Now we have the equation Z is equal to 1 plus BP divided by RT. From reduced pressure, we will get P, and from reduced temperature, we will get the value of T. By substituting those values in Z, we will get Z is equal to 1 plus BPC divided by RTC into PR divided by TR. Let's consider this as equation 2. From equation 1 and 2, we can say that Z is equal to 1 plus B to the power 0 into PR divided by TR plus omega into B to the power 1 into PR divided by TR. From this, we will get Z naught as 1 plus B to the power 0 into PR divided by TR, and Z to the power 1 is equal to B to the power 1 into PR divided by TR. The references for this PPT, Chemical Engineering Thermodynamics by J. M. Smith. Thank you.